Okay, people, let's make a start. So, few housekeeping things. All of these are the usual things. Remember, quiz 4 is due tomorrow. The only one I want to mention briefly is tonight I will put up 2 sample exams under scheduled final assessment. One of them will come with solutions, the other won't. That's our usual maths policy, that at most 2 sample exams, at most 1 set of solutions. If I were you, I would ignore these for at least a couple of weeks, right? At least until the last week of the semester. But from past semesters' experience, I know some people get stressed without having some idea of what they might see in the exam. So if you really want to take a look at them, feel free. Yeah, I'd probably, if I were you, leave them probably until SWAT-Vac or something, and then do them as dress rehearsal exams, right? But up to you how you want to do that. Okay. So, this is going to be our last seminar on probability. And we're going to talk about distributions that random variables can have. And so obviously there is a ton of these, but we're going to go through the real classics here, right? A bunch of really standard, discrete distributions. And the advantage of these is that if you've got a random variable which does obey one of these distributions, then a lot of the work has already been done for you, right? There'll be nice formulas for the expectation and for the variance, and there'll be all sorts of other analyses of various things. So if a random variable obeys one of these distributions, people will have studied it a lot and there'll be a lot known. So that's sort of why they're useful. And obviously the reason that these have been well studied is because they come up a lot, right? They either actually happen in the world exactly a lot, or they're very good approximations of things that happen a lot. So one of those 2 things. So I think we've got, well, probably really only 4 of these that are sort of interesting, 5 total. So the first of these is something we've basically already seen. It's a discrete uniform distribution, right? So remember that something happens uniformly at random if all the outcomes have the same chance of happening. A discrete uniform distribution, in particular, for a random variable, is when there's a bunch of consecutive integers from A up to B, and it's equally likely to take every value between A and B, and no chance of taking any other value, right? So here's a discrete uniform distribution with A equals 3 and B equals 8. It's equally likely to be 3, 4, 5, 6, 7, or 8, and it's no chance of being anything else. People understand this graph. This is the value it could be, and this is the probability that it has that value. So in this case, because there are 6 numbers, each has probability 1/6, right? That makes some sense? And so in general, this is the probability of any number is going to be 1 divided by the number of numbers. And the number of numbers from A to B inclusive is B minus A plus 1, if you work it out. And we have people have worked out the expected value and the variance of this. So the expected value is, I guess, unsurprisingly, the mean of A and B, right? The variance is the number of numbers squared minus 1 on 12. I'll show you in a minute how you get to that. But that's how that works. So discrete uniform distribution, a bunch of consecutive numbers, all of them equally likely. Does that make some sense? Okay, so that is distribution number 1. So let's look at a question. If x is a number selected uniformly at random from the numbers 100 up to 200, what's the expected value and the variance? Well, now our quick way of answering this is to say this is a discrete uniform random variable, right, with A equals 100, B equals 200. So using our formulas, we get that E of x is A plus B on 2, which is 150. Var x is number of numbers squared minus 1 on 12, which comes out to 850, right? But these formulas did not come from nowhere. So let me try and convince you that with enough work you could have figured out these formulas on your own. Let's actually pretend we didn't know these and quickly go through it. So our expected value of x, well, if we were doing that from first principles, it would be the probability of 100 times 100 plus the probability of 101 times 101 plus the probability of 200 times 200. But of course, all of these probabilities are just 1 on 101 because there are 101 of these numbers. And so it's just this. And then we just put in the formula for the sum of an arithmetic progression, which, if you remember, we proved by induction many seminars ago. And we get, I had too much come up at once there, but we get this as our formula for the sum of the arithmetic progression, and then when you work it out, it comes out to 150, just like our formula told us it would. And if you're prepared to do a little bit more work, you could even do the same with variance, right? This is what you'd get for the variance. Remember, for the variance, we have probability times the difference between our value and our expected value, which is, in this case, 100 minus 150 here, 101 minus 150 there, all the way up to 200 minus 150. Now, when you think about that, this is going to be negative 50, this is going to be positive 50, this is going to be negative 49, the term before this is going to be positive 49, and so we actually get this term here winds up being 2 times the sum of these squares. There's a formula for sum of squares of consecutive integers, which I think again we proved by induction at some point, and it's this, and if you work it out, you get 850. So details of there are not so important, but the point is that these things didn't come out of thin air. They can be worked out. For some of the distributions we'll look at, that's a bit of an effort, but it's possible, right? Okay. So, we've only done one so far, but this is my progressive attempt to keep these things separate in our minds. So the discrete uniform distribution, remember, that's where all the outcomes are equally likely, and in particular where it's a set of consecutive integers with all outcomes equally likely. Okay, so our next distribution is what's it like? It's like a, you know, single cornflake or something, right? It's not much good on its own, but it becomes useful when you actually put them together. So by itself, the Bernoulli distribution is just effectively a biased coin flip, right? Or maybe biased coin flip. So Bernoulli distributions, the only two things that can happen are 0 and 1, and it is 1 with probability p and 0 with probability 1 minus p. People sometimes with this distribution talk about a 1 as a success and a 0 as a failure, right? And notice, I should have, I guess, made this clear. With all of these distributions, in a sense, we're not just giving you one, we're giving you a whole bunch of them because they've got these parameters, right? So if we go back to the discrete uniform distribution, the parameters here were A and B. We get to choose the smallest number and the biggest number, and it's equally likely between these, right? So here, our parameter is P, and that is the bias on this coin flip. So we get a success, a 1 with probability P, and a failure, a 0 with probability 1 minus P. Expected value here shouldn't come as a huge shock. You can work this one out easily yourself, right? It's P times 1 plus 1 times P minus 0. So the expected value is just P. And likewise, easy to work out that the variance here is just P times 1 minus P. So as I said, not terribly interesting on its own, but we're about to see our next two distributions are going to be ways of putting Bernoulli distributions together, right? So, Bernoulli distribution, just possibly a possibly biased coin flip. Okay. So, we've got discrete uniform, everything equally likely. We've got Bernoulli, which is a biased 0-1 coin flip. Okay, so the first of the things we can do with a Bernoulli distribution is do a whole bunch of them until we see our first one. And what we're going to do is we're going to count failures before our first success. So zeros before our first one, or probability 1 minus P events before our first probability P event, right? Because of course, failure and success is relative here, right? We can define them how we like. So, in a network outage, what's a failure for the system is a win for the hacker doing a denial of service attack, or whatever else, right? You can pick your side here, but we are counting the number of failures before the first success. Now, important to be aware of, this is another of these annoying things where different sources do different things. So I think this is slightly the more common way of doing things, but you will also see some textbooks that include that first success, right? So their K will be different to ours, right? So that for them, a Bernoulli distribution would be the first success occurs on the kth thing, but that's not us, right? For us, a Bernoulli distribution is k failures before the first success. And so hopefully here, the probability calculation makes sense. So our parameter here is just P again. What's the probability that we see k failures before the first success? Well, it's going to be 1 minus P times 1 minus p times 1 minus p k times. That's the probability of getting k failures. And then a success, probability p, right? So hopefully this makes sense. And so this is what a geometric distribution with p equals a half looks like, right? There's a 50% chance that there's no failures before the first success, that you succeed first time, right? So there's a 50% chance it's 0. There's a 25% chance that there's one failure before the first success, because that's the probability of 0, 1. Then a 1/8 chance that it's 0, 0, 1, a 1/16 chance that it's 0, 0, 0, 1, and so on, right? Decaying by half every time. And so, in general, that's what a geometric distribution is going to look like, decaying by p every time. And it turns out these are slightly trickier calculations, or maybe a fraction, but the expected value for a geometric distribution is going to be 1 minus p on p. The variance is going to be 1 minus p on p squared. Right? So just depending on our parameter p. So, for example, if you have an extremely dodgy internet connection and every minute there's a 1% chance it cuts out, then how long would you expect to stay online? Well, this is going to be a geometric distribution, because we're interested in the number of, see here, failure and success is sort of backwards, right? We're interested in the number of minutes of uptime before the first cutout. We have a geometric distribution where our probability of success, which in this case is your internet connection cutting out, is 1%. And you can work out that the expected value of this is going to be 99 minutes. So you should expect to get an hour and a half or so before this cuts out. And you can work out the variance too. Okay, so I have a flux exercise for you. Just as a change, I'm doing this one as a word cloud. So the idea is type in what you think the probability is, something over something, something slash something. This is not an easy question, so I'll give you a little while to think about it. It's a good one to talk with people about, as they all are. Have I? Probably not. Oops, forgot that thing. Thank you. One thing to be a little bit careful of here, when we say the packet is received within the first 3 attempts, what does that mean about our possible number of failures? Up to 2, right? So if it needs to be received within 3, then we're only allowed up to 2 failures, right? So if you're thinking of a geometric distribution our possible number of failures is 0 or 1 or 2. Another 10 seconds. Okay. So I like this number here, 7999 on 8,000. That may well be equal to this thing here. I don't know, but let's work our way through it. Judging by the quantity of answers of that, I'd bet it was. Okay, so there's at least 2 ways of coming at that. I'm going to do probably the more difficult way first, or at least I'm going to show you sort of the way straight from the geometric distribution and then a bit of a shortcut. So if we just thought of this as a geometric distribution question in the most obvious sense, we'd think, okay, each time the packet is set, that's a independent Bernoulli trial. I should have really emphasized, right, when we're talking with the geometric distribution, obviously these have to be independent Bernoulli trials where we're doing this. Okay, is an independent Bernoulli trial with probability of successful transmission 0.95. So we're 95% chance of flipping a 1, 5% chance of flipping a 0. So k be a random variable whose value is the number of times transmission fails. So this is our geometric random variable. And then we've got a geometric distribution whose parameter is 0.95 or 19 on 20. And this isn't part of the solution really, but our expected value is 1 on 19, so we're not expecting many failures here. We should be very likely to do this. We're interested in the probability that x is less than or equal to what? 2, right? Because at most 2 failures. And so that's the probability that x is 0, or x is 1, or x is 2. And we can plug them in to our formula. Probability that x is 0 is this, probability that x is 1 is this, probability that x is 2 is this. And if you work your way through it, you get 7999 on 8,000. So that works perfectly. There's another way to get at this, which is to say, well, the probability that x is less than or equal to 2, that's 1 minus the probability that x is greater than or equal to 3, right? The probability that we have at most 2 failures is 1 minus the probability that we have 3 or more failures, right? And so here, probability of 3 failures is 1 on 20 cubed, 3 failures to begin with, which is 1 on 8,000. And so subtracting that from 1, we get that answer again. Make some sense? So either way gives you the same result, which is a relief, because they should. Okay. So geometric, our very rough intuition for that is the number of losses before the first win, or, excuse me guys, thanks, is the number of losses before the first win, or in other words, the number of 1 minus p probability events before the first p probability event in a series of independent Bernoulli trials. Gerontology being the study of aging, of course. I sort of like that maths was right down the bottom. Okay, so we've got another distribution which people sometimes get mixed up with the geometric distribution. So let me talk about the differences between the two. Right, so a binomial distribution is where, remember, geometric, we were doing something some uncounted, unspecified number of times until we first had success, right? Binomial, we decide ahead of time how many times we're going to do something, and then we count the number of successes in that sequence. Right, so binomial, what we're doing is we pick an n and a p. The p is what it always is. It's our probability that our biased coin comes up 1. Right, the n is the number of times we're going to flip that biased coin. Right, so you decide on those 2 parameters, and then you count your number of successes, right? This is the formula for the probability that we get k successes. I'm going to talk about why that's the truth on the next slide. We expect overall NP successes, which perhaps makes a bit of sense. You know, if you're rolling a dice 60 times and you're interested in the number of times you roll a 6. It's about 1/6 times 60 is 10, sort of makes sense. Turns out the variance is this. This is what a binomial distribution with p equals 1/2 and n equals 20 looks like. What does this remind you of? So it's sort of like a normal curve or a bell curve. There's actually two reasons why it's not like a normal curve or a bell curve. The first is really obvious, which is that it's discrete. If this was a proper curve, then we'd be able to get 10.5. But here we absolutely can't. But also, even if you drew a nice smooth curve through this, it wouldn't quite look like a normal distribution, right? Wouldn't quite look like a proper bell curve. The reason being that it gets closer and closer to a bell curve as your n gets really big, but for small values of n, it's not quite right. It's not quite there. Okay. And there's the theorem that says it gets closer and closer to a bell curve as n gets large. Okay, so let's talk for a minute. So I'll say this 6 times in this lecture, but that's okay. Let me remind you, geometric, not this one, we do something until the first success, and we're counting the number of times we do it until the first success. Binomial, we decide ahead of time how many times we're going to do something, then we count the number of successes. So they're measuring different things, right? Okay, so why is this our formula? So let's look at an example. So if x is the number of 6s we get when we roll 5 standard dice, or if you like, when we roll a standard dice 5 times, right? Then this formula tells us that our probability that x is 3, that we roll 3 6s, is 5 choose 3 times 1/6 to the power 3 times 5/6 squared. So why is that? Well, if you think about 1/6 to the 3 times 5/6 squared, that's going to be the probability of rolling 6, 6, 6, less than 6, less than 6, right? Because 1/6 cubed is the probability of rolling 6, 6, 6 in our first rolls, then 5/6 squared is the probability of rolling less than 6, right? But notice that that's the probability of rolling it in that order, of rolling 6, 6, 6, less than 6, right? But we're interested in all the ways we could roll 3 6s, right? And we could do that in lots of different ways. Here they are. 6, 6, less than 6, 6, less than 6, blah, 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 blah. I hope I've got them all there. Now, how many of those ways are there? Well, we've got to pick 3 of our rolls to get 6s on out of 5 rolls total. Number of ways to do that is 5 choose 3, right? And so that's why we have this factor of 5 choose 3, and that's why our formula comes out as that. Does that make some sense? And of course, if you just generalize that argument, there's nothing magical about a 6th or 5 or 3 here. You get that this is our formula in general. Make some sense? Okay. So there we are. That's the binomial distribution. Okay, good. And we've got these 2 formulas for expectation and variance. So, for example, if 1,000 people search a term on a certain day and each of them has a 10% chance of clicking on a sponsored link, that's probably about 1,000 times too high or more, then the number of clicks on that link is approximated by a binomial distribution with n equals 1,000. So we've decided ahead of time how many times we're doing this trial, right? 1,000 people in the day. We're interested in how many of them are successes, how many of them click the link? Well, each time that's a 1/10th chance of doing it. So we can then calculate the expected value of clicks on the link would be 100, and the variance would be n times p times 1 minus p, which is 90, which is not really high, right? That means it's bunched up pretty tightly around this 100 value. It's not going to be too far from that. Okay, so another question. So a factory aims to have at most 2% of the components it makes be faulty. Every day, or it does a quality control test of 20 random components. What's the probability that 2 or more of these will be faulty if it's doing exactly what it says it will, if it's exactly meeting its 2% target? So this is, what are we doing? Well, each component is going to succeed or fail independently of the others. So we're doing 20 Bernoulli trials, and we're interested in the number of successes or failures, right? So this is a binomial distribution, right? Because we've fixed our number of things, we're interested in the number of successes. So x be a random variable that counts how many of these components fail their test. So here we're flipping failure and success. We're counting the number of failures, right? So each component fails with a probability of, well, if it's meeting its target, then exactly 2% chance that a component fails the test, right? And what are we interested in here? We're interested in capital X being what? So we're interested in the probability that 2 or more are faulty. So we're interested in the probability that capital X is at least 2, right? So we want to know, is X greater than or equal to 2? What's a good way of trying to work this out? Yes, so it's going to be a pain to add up the probability that X is 2 and 3 and 4 and 5 and 6 and all the way up to 20. It's much easier to say, well, this is the complement of X being less than or equal to 1. So we can work this out as the probability of 1 minus the probability that X is less than or equal to 1. In other words, 1 minus the probability that X is 0 or X is 1. And now we can just sub into our binomial distribution formula, right? So the probability that this is 0 is 20 choose 0, which of course is just 1, p to the 0, 1 minus p to the 20. Probability that X is 1, 20 choose 1, p to the 1, 1 minus p to the 19, right? And if you do the sums here, you get about 0.94, meaning that there's about a 6% chance that we have 2 or more faulty components, right? So again, just subbing into the formula that defines our distribution, right? Okay. So, discrete uniform, everything equally likely. Bernoulli biased 0-1 coin flip, geometric, number of failures before the first success for some definition of failures or success. Binomial, number of wins from a fixed number of tries of a Bernoulli distribution, right? We've got one more to go. Very quickly though, which of these is the best model for a spin of a roulette wheel? I'm only going to give you about 30 seconds for this one. Another 10 seconds. Okay, so I agree with this. So it really can't be, so Bernoulli doesn't make sense because then there'd only be two values and roulette wheels have more than two values. And it really can't be geometric or binomial because both of them involve doing something over and over again, right? Whereas this is just one spin. So roughly, hopefully, in a decent casino, your roulette wheel is giving you a random number between, I'm not a roulette player, 0 and 60, is it? 0 and whatever. Yeah, okay. So, we've got one last one to go. This one's a little bit trickier than the others, called a Poisson distribution after the French mathematician. And very roughly, the way to think about this is where we have an average number of events that occur in a particular time period, and but that average will vary. So classic examples are things like number of calls coming into a call center, that kind of thing, right? Where we have number of faults of a machine in a given time period. You know, it'll have an average, but it'll sometimes be bigger than that, sometimes be smaller than that. So this is called a Poisson distribution. The actual way to think of it is imagine that, like with calls to a call center, imagine there are a huge number of people out there, but they all only have a very small chance of making a call to the center. This is what then happens in terms of the number of calls at the center. Okay, so it's got this slightly funky looking definition in terms of the probability that x equals k. It's got Euler's number in there. The only parameter here is lambda, where lambda is the number of things we expect in our time period, right? So unsurprisingly, its expected value is lambda. Its variance, it actually turns out, is also lambda. And it looks like this slightly sort of bent normal distribution, right? Can never be negative. It can be really big, but its chances of being really big are really small, right? Okay. So if a call center usually gets 6 calls a minute, then it's going to be fairly well approximated by a Poisson distribution. Obviously, it expects to get 6 calls a minute, but the variance will also be 6. So there'll be some chance it's less than that, some chance it's greater than that. Occasionally, it'll be miles bigger than that. Poisson distributions never give less than 0. Not really a funny cartoon, but good to remember. Okay, so question 25.3 says the number of times a machine needs adjusting during a day approximates a Poisson distribution. On average, it needs to be adjusted 3 times per day. How many golden days where you don't need to adjust it at all do you get? What's the probability of a of having a wonderful day where it doesn't need adjusting? Well, let x be a random variable that counts the number of adjustments a day. This is going to be a Poisson variable. We want to know the probability x equals 0, right? We don't have to adjust it at all. So x has a Poisson distribution, and what's our lambda here? 3, absolutely, right? Because we expect to have to adjust it 3 times. That's our lambda. So we want to know the probability that x equals 0, and just plugging that into the formula for the Poisson distribution gives us this. So this is e to the negative 3, which is about 5%. So you're not going to get too many days where you don't adjust the machine, even though you usually only adjust it 3 times. Okay, one last final important fact is that if something is Poisson distributed and it stays being Poisson distributed, then the number of times it happens in a different time interval will also follow a Poisson distribution. So for example, with a different value of lambda. So for example, if the number of requests to a server in any hour of a day is Poisson with lambda equals 100, then the number of requests to the server over 24 hours will be Poisson as well, but now our lambda will be 2400, right? And assuming it goes right down to the smaller time increments, the number of requests to the server in a minute will be Poisson with lambda equals 100 on 60, right? So Poisson distributions are sort of time invariant in this sense, right? To scale it, you can just scale your average number of things. Okay, so all the things we said before, Poisson is often the number of events in a fixed time period, right, where we have a particular average. Okay, very last flux question, then we're done for the day. Again, a fairly quick one. Give you another 30 seconds. Okay, good. So this is Poisson. Just to talk through it very quickly, obviously it's not discrete uniform, right? We're not going to have some number of fixed numbers between blah and blah which are equally likely. That's crazy. It's not only going to be 0 and 1, so it can't be Bernoulli. Geometric might be the amount of time before someone gives birth or something. It's not going to be that. Binomial would be a reasonable answer if we knew the number of expecting mothers out there. Maybe we could say binomial, but I don't have that figure in my head. The best one is Poisson. This is sort of the same as calls to a call center, except a bit more important. These are random arrivals to a particular thing, right? Existence, perhaps. Okay, thanks, people. I will see you Thursday.